Okay, it is really a pleasure to be here, and I remember ICAP really as my first big conference, and it was really an eye-opener to me, and so I'm really honored to be able to speak today here. I will talk about testing the isotropy of space using a Michelson-Morley test with electrons, and I hope during my presentation it will become clear what actually a Michelson-Morley experiment with electrons looks like, and probably you will realize that many of you have actually done this already. So here's the outline of my presentation. I will start with an introduction and then briefly touch on to Lorentz invariance tests, which are actually a generalization of this testing isotropy of space. And then I will discuss how we actually implement a Michelson-Morley experiment with electrons. And finally, I think this is the most fun part of this project, at least it was for me, was actually thinking about what this all means. So we all know the Michelson-Morley experiment that was originally designed to look for the so-called ether. We know now that, and we understand that it's actually not there, but it's, I want to start there. So what Michelson-Morley did is they took a light beam, and it was not a laser beam at the time, and they collimated it very carefully and then split it and then had it bounce around 5 times before they recombined it and looked here at the constructive interference. They adjusted the interferometer carefully and then rotated it and looked whether the constructive interference stayed there. And what we know is that actually they didn't see any change of the interference, any shift, and from this we can actually conclude that Lorentz symmetry is already maintained at the 10 to the minus 9 level. This was a quite important result, and as a consequence, many people improved this test over time, really checking whether the isotropy, whether the speed of light is isotropic in space. And you can also see here what I find quite remarkable is that this was the invention of the laser. It did not really have a big impact. Very recently, there has been quite some activity trying to improve these Michelson-Morley experiments further, and there is a motivation here, and this comes from the fact that at this level of precision of 10 to the minus 17, that this corresponds to the ratio between the weak mass scale and the Planck mass. And there are some theories which actually predict that Lorentz invariance might be broken at the Planck mass, and then there is some mechanism which actually would restore it at lower energy scales. And if you do then perturbation theory, you would expect that on the order of ratio of energy scales, and this here is this energy scale, the smallest reasonable energy scale we know of. So how do these tests look? Now the modern ones, you have a cavity, actually 2 cavities orthogonal to each other. You take a laser, 2 lasers, you lock them individually to the cavities, and then you beat the 2 lasers and look for any frequency variation. So this is how you do nowadays a test with light. However, we know that Lorentz symmetry should not hold only for light, it should hold actually for any particle. In particular, we are here concerned with the electron, and that means, for instance, that the maximum attainable speed should be the speed of light. And also, moreover, which is maybe more important, is that the energy of an electron moving with a specific velocity or momentum should not depend on the direction it moves in. So this is the kind of test we would like to do. There have been already tests of Lorentz symmetry in various contexts. One interesting thing is that accelerators work only because Lorentz symmetry holds at the 10 to the minus 10 levels. Otherwise, we would have to tune our accelerators differently. Optical cavities are already mentioned. There are also spectroscopy tests, and one of them is actually was carried out by Dima Budka and his collaborators in Berkeley. I will mention this test a little bit later. And there are also astrophysical observations where it is shown that electrons don't move faster than the speed of light. So The question now is how do we test Lorentz symmetry for electrons? How do we verify that the energy dispersion relation of the electron is independent on its direction of motion? So what we want to do is kind of a Michelson-Morley interferometer for electrons. So here's a Michelson-Morley apparatus, and one thing to notice is that we get the interference will depend on the phase of how these beams combine here, and what we have there is actually two standing waves. So kind of the idea is now what we need to get at are standing waves for electrons, and down here is actually a nice source for standing waves of electrons, and those are electron wave functions in atoms. And then the whole experiment consists in actually creating such an arrangement where we have a superposition of two standing waves which are oriented in a orthogonal direction. That's the whole idea of the experiment. We use actually calcium-40, and in particular the metastable D5 level, which Rainer Platt already introduced, which is a nice, or can serve as a nice qubit. And the two levels we are going to look at is the MJ1/2 and MJ5/2 in the D5 manifold. On the right, you can see how these wave functions actually look. And you can here see that the momentum expectation, that the electron moves predominantly in this direction. Here it moves predominantly up. And this is actually the basis of this mechanism. And then basically what we have to do is measure the energy between those two wave functions to get actually the phase information. So this is now how the full experiment could look like. We create this superposition, and if there is a preferred direction in space, drawn here as this tensor, we get a certain energy shift due to this. But if the Earth rotates, and I guess we humans have learned to be humble, we don't expect this preferred inertia frame to rotate with the Earth, then actually this energy shift, or there should be the energy shift between those two levels should actually be changed, and it actually should be modulated with the Earth's rotation. And when you look careful, you see if I turn it upside down, I would get the same situation. Therefore, I expect actually an energy modulation of 12 hours. So here's now the experiment. We initialize our ion with the methods Rainer explained yesterday in a ground state. We apply then a pi/2 pulse and move the population into this MJ1/2 state. We apply then a pi pulse on the other, and move the remaining population up into the excited state. However, there's a problem. And the problem is that those two states have very different magnetic momenta. And that means that magnetic field fluctuations will introduce an energy shift. They will cause noise in the phase evolution. And therefore, this doesn't work very well. The way out of it we came up with is actually to use something which is known in the quantum information community as a decoherence-free subspace. So if you have, for instance, a state like this, and you analyze it, so here one ion is in a -1/2 state, and the second ion is in a 1/2 state. And when you look at this, the wave functions look very similar. So they have, or they look similar, the momentum, and therefore they have actually the same sensitivity due to this background field. However, the magnetic moment of this part of the superposition is actually 0 if you assume a global homogeneous magnetic field. Of the other part 2, therefore, if the magnetic field is changing, the relative energy of the two states is not changing. So that is the whole trick. And you can see the consequences of this here. What I show here is Ramsey fringes, so pi/2 pulse, some waiting time indicated on the x-axis here. And then another pi/2 pulse. You can see for ion number 2, it oscillates because we are slightly detuned. There's a small magnetic field gradient. For ion number 1, we are perfectly on resonance. But you can see after 1,000 microseconds, actually, there's no contrast left any longer. However, if I look at the correlation of the excitation, I can see fringes going on. And in fact, they go out to 100 to 500 milliseconds. And in other experiments carried out actually in Innsbruck, we have shown that these oscillations can extend up to 30 seconds if you go to the ground state. So this is the idea of a decoherence-free subspace. And that is good because it allows us to use much longer Ramsey times and therefore gain sensitivity. So here's the protocol now. We have two ions. We laser cool the ion string, and then we apply this pi/2 pi pulse on both ions simultaneously to create our states, hopefully sensitive to Lorentz violation. We wait 100 milliseconds in our experiments, and we do the inverse to close the interferometer, and then we do the state readout. And we do this over and over, and we do this while the Earth is actually rotating our apparatus. The magnetic field is fixed with respect to the Earth's surface, and that actually changes the orientation of the states we create. And therefore, what we would expect, if there's a Lorentz violation, that it would modulate the energy shift or the phase of our interferometer. This is the data. The gray data point are estimates from 100 experiments each, and then we bin this for over an hour to get these blue data points. This data was taken for 23 hours, and what we do then is then we fit this to a model. If there's no Lorentz violation, we would expect a straight line. If there's Lorentz violation, we would expect a 12-hour modulation, modulo some higher order corrections. And by then looking what kind of amplitude we get out of this fit, we can put a bound on how strongly Lorentz violation is, or how small it must be, what is compatible with our data. What we find is that the energy shift is 11 millihertz. So we find an energy shift which is consistent with 0, and the uncertainty is 11 millihertz. What does that mean? So we have to compare this energy shift to an energy scale. And actually it turns out that intuitively the energy scale we have to compare to is actually the kinetic energy the electron has in this state. That's around 50 eV. So the sensitivity is on the order of 10 to the minus 18. That's a very hand-waving reasoning, and you can go, for instance, to Mariana, who will explain you more carefully what you have to do, and you have to evaluate a matrix element, and Mariana and her collaborators actually can do this, and then you come up with this number too. What we found actually exciting is looking at the Allen deviation, that we basically continue to average down about a factor of 1 to 2 above our quantum state projection noise, but there are no signatures of long-term systematic drifts of this test. And that is actually very promising if you actually want to look more precisely about things. So what does that mean? Here is a plot of previous Lorentz invariance tests for electrons, relative precision. There were some, actually from these rotating resonator or cavity experiments, you can also derive a bound. The best bound was actually this dysprosium experiment Dima mentioned before at just a little bit above the 10 to the minus 17. What this work I just presented improved on that bound on the, about a little bit more than an order of magnitude using this trick of a decoherence-free subspace, essentially. So I want to switch now gear and talk a little bit about what that actually means, and that was for me actually the interesting part. What we realized relatively quickly, and I think as an experimentalist we all know this, that you need to pick a reference if you actually measure something. So, and the implicit assumption we sort of made is that the Coulomb force is actually isotropic. So if we would have seen something, we probably would have just jumped to the conclusion, oh, the electron violates Lorentz invariance, or space is not isotropic for the electron. But that's not true. We don't know. Maybe the binding potential was not isotropic. And that could be, for instance, the reason, or the reason for this could be, for instance, that the photon has its dispersion relation is not isotropic. So this is depicted here. Here we assume the electron is squeezed in one direction, and here it's actually the Coulomb potential. So those are two alternative views of if we had seen something. And so the conclusion of that is that what we have not done is really a test of the electron dispersion relation of the isotropy, but actually of the ratio of the electron dispersion relation and the photon. So let's revisit the Michelson-Morley experiment. and let's look at it. So if somebody would have seen something, the natural conclusion would have been, oh yeah, the photon maybe travels in the vertical direction faster than the horizontal direction. But no, there's a different solution. It could be that simply the arm got shorter in this direction. And actually, there are reasons why this could be. And one reason is actually, yeah, one has to think of what determines the length of this arm. And one reason is actually that the Coulomb force maybe could be different in this direction than this direction. If you're so crazy to assume that the dispersion relation changes, why not this? And so this would be a possible explanation. It turns out that the length is also determined of these arms by the molecular bonds, where not only the Coulomb force enters, but also the electron dispersion. Conclusion from this is, if you do a Michelson-Morley experiment with photons, you're going to test essentially also the ratio of the electron dispersion relation to the photon dispersion relation. So therefore, we need to evaluate our experiments in the context of the Michelson-Morley, classical Michelson-Morley test with photons. So we put our work on the same plot I've shown in the beginning, and we see that we improved at the time about a factor of 5 over the best bound at the time. I should mention that very recently the Tobak group has now a value for rotating resonators of similar order. So these two tests confirm Lorentz symmetry well beyond the bound of the weak interaction scale to the mass, to the Planck mass. So where to go from now? So that basically we didn't find anything unusual. Can we push these tests further? One thing I should stress is we actually so far tested only for the isotropy of space. We did not really check for whether the Lorentz boosts are also affected, so whether Lorentz symmetry holds also when we change the speed with which we move through our universe. And one way to do this is to measure during a year. And what happens is that the Earth, basically, while it revolves around the sun, and the sun moves throughout the galaxy, you're modulating the speed of the Earth through some virtual preferred reference frame. And by doing this measurement at multiple points during the year, you can also place bounds on this. You would like to place bounds on this violation on the order of 10 to the minus 22, on the order of 10 to the minus 17 or 10 to the minus 18 too, right? So, but since the speed with which you modulate this relative velocity to the preferred, to a potential preferred inertial frame is much smaller than the speed of light, turns out to be on the order of 10 to the minus 4 of the speed of light, what you need to do is you need to improve the sensitivity by 4 orders of magnitude over this 10 to the minus 17, 10 to the minus 18, so you really need to go to 10 to the minus 22. What can you do about this? You can take more statistics. So we just took 1 day of measurement and we got already a competitive bound, so you can think, oh yeah, let's measure a full year, but that gives you only an order of magnitude. So that's not really such a big help. So we need to turn to something else, and Vladimir Zuba and Mariana looked at this, and so we looked actually in particular at the ytterbium ion here, and it turns out that the F state is 14 times more sensitive than calcium. And the reason for this is that this F state is actually a whole state and has the electrons there have a much higher kinetic energy, and that boosts essentially the sensitivity because the energy shows up in the denominator. In addition, this F state has a very long lifetime of, really, really long, beyond anything which is experimentally relevant, and that allows you in principle to make a much longer Ramsey interrogation time. And since we have seen in other experiments that you can maintain in the sequence-free subspaces coherence for 30 seconds, it's reasonable to assume that you can do at least that well if you use a special, if you start shielding magnetic field gradients. So overall, from this, we expect that we can gain another 2 or maybe even 3 orders of magnitude. And in this paper down here, we estimate that we should achieve with ytterbium a precision of 10 to the minus 22. What about systematics? We looked at it. We couldn't really come up with anything but something weird like an anisotropic black body shift. Turns out that that black body shift is rather small because the electron is strongly bound in ytterbium, and we estimated that to be 10 to the minus 22 per Kelvin, which actually shouldn't be a real problem. So what would you have to do? This is where it gets a little bit more tricky. One, the maybe conceptually easiest way would be to drive this S to F transition. That's the famous or infamous Octuple transition. It's quite hard to drive, but nevertheless, PTB and NPL are really experts because of their work on atomic clocks. And they have some coherent, or they have coherent control over this transition, and they could produce those states, which are then, these are superposition states of the same manifold in the F state, which would be then sensitive to this Lorentz invariance at a much, would be much more sensitive. But there are maybe also other methods to produce these superposition state in the F state. In particular, we are thinking about some ideas how to shelve into the F state, then do some optical pumping here on various lines, and then using radio frequency and microwave pulses to generate something, a state which actually would be sensitive to these states, to these imperfections or these to Lorentz violating effects. So I want to sum up here now. We use the decoherence-free subspace to test for the isotropy of space. So this is a nice application of the toolbox of quantum information. We have in the past learned a lot how to control quantum states, and I think it's really a great opportunity to take this control and actually do physics with it and, for instance, search for exotic effects. We improved using this technique on the best test for the electron, or if you term it, if you name it differently, for electromagnetism. And I presented also our ideas to improve the precision of these tests by 4 orders of magnitude using ytterbium. I should also mention, I guess Mariana mentioned this also, that using highly charged ion, one can get even more sensitive. Simply, again, the argument is that the kinetic energy of the electrons will be higher in highly charged ions. With this, I want to thank you for your attention and also my group, in particular Hong and Mike or Thanet Putivarazin, who carried out the experiment. What I didn't mention is that from actually really going for this experiment, thinking carefully how we want to do it, till producing the data I've shown you was just 3 months. So this is a really fantastic timescale for a precision experiment, and that was only possible because we had already a good understanding of our apparatus, and also because those 2 guys are really phenomenal physicists. And we had really great theory support, which helped us understanding what we were doing. Michael Hornsey at the time at the Miller Group, and Mariana, Sergey, Ilya, and really helped us understanding what is the matrix element and learning more what this all means. And I acknowledge also collaboration with Victor Flambaum and Vladimir Zuba, who then actually looked with us then together with Mariana and her collaborators into which other elements we can use or which other ions we can use to improve those tests. Thank you very much for your attention.
So thank you for finishing ahead of time. And any questions, please? Yes, please. Okay.
Yeah, so they rotate, I mean, I don't know really the numbers, so I would have to guess, but I guess it's less than 10 minutes. But the thing, I mean, one thing I want to maybe say at this point is the nice thing about atomic systems, they have really long-term stability. You don't have really this typical problem of 1 over F noise craziness. And to connect back to our previous speakers of this session, I think that makes atomic systems fantastic candidates for searching dark matter, light dark matter, where these oscillations will be rather slow. And so that is also a natural connection. Many dark matter models actually predict Lorentz violation. So by looking for these things, we do some sort of dark matter test, but this has not been really worked out yet.
Okay, any other question? Oh, yes, yes, please. Okay. Oh.
Yeah. Yeah. So the vector-like interactions are, the bounds are much more stringent, if I recall properly, like 10 to the minus 30 plus. The argument, so I discussed this, for instance, with Holger Müller, and he says, we really don't know what we are looking for. We have no guidance. So all we can do is can test everything possible. And that is kind of the state. I mean, and I'm also not really in the right position really to answer it, but that's also my feeling. I mean, we have no orientation. And so all we can do is can push some numbers. Of course, it would be nice if you would have guidance. Like for the EDM, there's a great guidance there. So there are theories beyond the standard model which predict something. And here, it's all very vague. And so that's, I think, the answer.
Okay, any other question? Okay, so if there are no other questions, I mean, let's thank all the three speakers for the fascinating talks. Okay.
Okay, we have three short announcements. The first is we have 20 or so seats available for tomorrow's DMZ tour. And for those who register for the Thursday banquet, please come forward to the information desk to pick up your ticket. Okay, and lastly, for those who are attending the International Advisory Committee meeting, please come forward to the podium so that we can move together. Thank you very much. Enjoy lunch and posters.